Hi everyone, I hope you are doing well. So in today's video, I'll be going through the 2022 physics exam for the Northern Hemisphere multiple choice section. Like always guys, before I start this video, if you guys want private tutoring in specialist methods, physics or chemistry, you can always email me through this email. And yeah guys, let's smash through this video. Question 1. Two parallel plates that are 10 millimeters apart have a potential difference of 5 kilovolts between them. Which of the following best gives the strength of the electrical field between those plates? Easy. So the formula should come to your mind is, let me have a look at my summary sheet, is V is equal to ED. And we want to find E, where this is the electrical field strength. So V over D. And that's going to be what? So the voltage, which in this case is 5 kilovolts, you want a 5.0 times 10 to the power 3 to turn it into volts. And distance has to be in meters, so it'll be 10 times 10 to the negative 3. Putting that in our calculator, that gives us 5.0 times 10 to the power of 5. So it looks like D is your answer. Easy. Question 2. A loudspeaker consists of a current-carrying coil with a radial magnetic field as shown in the diagram below. The direction of the current in the coil is also shown. Okay, we're showing that direction of current. Okay, which of the following best describes the direction of the force on the coil? Alright, let's have a look. So just have a look over here. We can see that the current direction is actually down here. That's where the current direction is. And we can also see that the magnetic field there is actually from, remember, this is your north to south, so it will be to the right. So using your right-hand slap rule, so you remember your thumb is going down where the current is, and your fingers are going to go to the direction of the magnetic field, which is to the right. Hence, your palm should be right into your face, which is out of the page. So that is the force. Out of the page, which looks like A. And you can do it for many, like for example, you can do it to any side. So for example, let's rub this part off. And that's the way over here. Well, the current's of course going to go here. So that's your current. And we know that this is going to go downwards, your magnetic field, and do it again. So thumb goes to the left and your fingers go downwards, and hence your palm should be into your face. So out of the page. Easy. Question 3. The gravitational field strength at the surface of a uniform spherical planet of radius r is g. At a distance of 3r above the planet's surface, the strength of the gravity will be closest to what? So let's just draw a nice figure over here. So we know this is the planet, and our distance, this value is g. But if we go 3 times the r above the surface, somewhere around here, so 3r above the surface, what will be the value of g here? That's what we want to calculate, which in this case is just a, right? A, so we don't get confused. Well, we know that this from here, the distance from the center of these planets is what? It's going to be 4r. So let me just draw it nicely. It's not the most nicest, but yeah, this here will be 4r. Let me drop it like that. It'll be like this. So this will be 4r. Done. And so, yeah. The way that I would do this question is by using this formula over here. This kind of question is always repeating in every exam, and this is the formula that I like to use. And so it's this one over here. Let me write it down. G1 over G2 is equal to R2 over R1 squared, where G1 is like the first case. So we know that when the radius is r, the value of g is actually just g. So your G1 is just going to be g. We want to find G2, which is this case here, is equal to your radius 2, which is for this radius over here, which will be 4r, all divided by the radius 1, which is this r over here, squared. And so these will cancel out, and then the force being squared, which is 16. So if we, so this G2 is actually just G over 16. That is your answer, which is D. That is the gravitational field strength at 4r from the center. That's your G value. Easy. Question 4. The Mars Odyssey spacecraft was launched from Earth to explore Mars. The graph below shows the gravitational force acting on a 700 kilogram Mars Odyssey spacecraft plotted against its height above the Earth's surface. Alright? Which of the following is closest to the minimum launch energy needed for the Mars Odyssey spacecraft to escape Earth's gravitational attraction? Well, this is the, gravitational force, and this is the height of the surface. We can see that at 24 times 10 to the power of 6 meters, it does escape Earth's gravitational attraction, as there's no more gravitational force applied. As you go further, there is no more gravitational force from that onwards, forwards. So all we need to find actually is the area under this graph, the whole graph. And to do that, because it's not a very smooth graph, we'll just find the area of one square and start counting the squares. So the area of one square is what? Is just 1,000 newtons times 3 times 10 to the power of 6. Remember, this is to the power of 6. That's going to give us the area of one square. 3 times 10 to the power of 6. Which gives, oh my god, it is a very, very big number. Or we can just write it as 3.0 times 10 to the power of 9, because this is 2 threes. And you can write that as you can write that 1,000 ends 1.0 times 10 to the power of 3. You multiply these powers add up. Yeah. If I'm not mistaken. 1, 2, 3, 4, 5, 6, 7, 8, 9. Beautiful. So that's what we have. This is the amount of energy in one block. And what we're going to now do is to count the number of squares. For example, so we have 1, 2, 3, 4, 5, 6, 6. This is 7, including this little one here, 7. 8, including this little one here. 8. We will say 9 with this 2. It's going to be 9. 10 and 11. Wait, am I about... Wow, it's actually more... What have I done? Have I just done myself a miserable job? Did I count up? I want to count it properly. I just did it very quick. Sorry. So let's just schedule. So this is 1 of the squares. 2, 3, 4, 5, 6. 7, including this little part here. 7. 8, including this little part here. 9, including this part here. 10, including pretty much this part over here. 11, including pretty much this part. And approximately 12. Approximately 12, we'll say. Around the 12, yeah. So we're going to write just 12 of these things are going to be that. So what's times that by 12? We get 3.6 times 10 to the power of 10, which looks like the closest is C, which is 4.0 times 10 to the power of 10. Yeah, nice and easy. Hope that's correct. And yeah, let me rub that out. Alright, have I done any mistakes yet? Looks all good. Question 5. Let's have a look at that. The ratio of the number of turns in an ideal step-up transformer is 350 to 1. An alternating RMS current of 30 milliamps is supplied to the primary coil. The RMS current in the output will be closest to what? So let's just draw a transformer here. Oops. This is where, of course, your power supply is coming out. And here is, let's say, your... because it's a step-up transformer, why is it 350 to 1? It's supposed to be 1 to 350. 1 to, the number, of course, 1 to 350. Because, yeah, it's supposed to be 1 to 350. It's step-up. The number of coils on the primary should be less than the, so this has to be small and this has to be large, because remember, you're taking little voltage and you're stepping it up. So, yeah. So that's the numbers. An alternating RMS current of 30 amp is supplied to the primary coil. So we know that in this primary coil over here, we have 30 milliamps. And what we just want to find the RMS current in the output. So this part here. What's the current here? Easy. Well, we know that the number, so number of primary to the number of secondary is equal to the current in the secondary divided by the current primary. And so we want to calculate, remember, the secondary. So what's NP, which is 1, over 350, equals IS is what we're trying to calculate, the secondary, and IP, which is 30. And why am I writing 30 and I'm not converting it to milliamps is because all of these answers are in terms of milliamps. So it makes my life easier to not convert. And so what's that going to be? So 1 over 350 times 30, that gives me 0.085, which is approximately B. Done. Question 6. The two concentric loops of conducting wires are placed on a flat horizontal surface. The outer loop contains an open switch and a battery cell. The inner loop consists of a single closed loop of wire. The diagram below shows the arrangement of two loops as viewed from above. Which of the following best describes the induced current in the inner loop once the switch is closed and the outer loop as viewed from the above? So this is actually, we're talking about Lenz's law here. So if this switch is actually now closed, we're going to start to have current going in this direction. Remember, the longest side is where current's going to start. That's the positive terminal, and that's the negative. So current's going to be starting to go this way. Yep. If you use your right-hand grip rule, for, let's say, in this example, the current going this part over here, we can see that your hand's going to be gripping, your hands, so using your hand like this, there should be open circle here, because you remember the current, the magnetic field line should be coming out when you do the right hand grip rule, while your thumb's in this direction of the current. So it means that these are all going to be X's. This is where the magnetic field lines are going to be coming out. So these are going to all be X's. Yep. And so all in the inside is going to be big, like circles. I'm just going to draw big circles pretty much. Big circles, all inside that loop, including that little one. Now, by Lenz's law, this actual magnetic field, what Lenz's law does is it opposes that magnetic field, that magnetic flux, and yeah, to oppose it, if it's going inside, so can you see how it's going out the page inside? It's gonna try to oppose it, so it's gonna have an induced magnetic flux that's gonna be out of the page. Magnetic field that's out of the page. So not out the page, sorry, into the page, because this is already out. So to oppose it, it's going to do into the page. So imagine rubbing this whole part off, and now it's going to be into the page. So big X's now, all inside that loop. And so now to know that where the direction of the induced current is, you just use the right hand grip rule and put your thumb where the X's are, where the magnetic field is going. So putting your finger right there, you can see that the current should be turning clockwise. So clockwise, there should be some induced current that should be turning clockwise here. So which of the following best describes the induced current in the inner loop once the switch is closed? As shown from the above, it should be clockwise. So not B or D. Is it steady or momentary? It's going to be momentarily. Remember, for magnetic, for a continuous current, you need to be keeping motion. Like for example, all the experiments done in Lenz's law, you're moving. For example, you're moving a magnet. As you move it, it's going to be opposing it. So you have to just keep moving it to create induced current. In this case, they've just put it there, and no one's moving it. They've just put these two concentric loops, and for momentarily there will be clockwise current, and that's it. It'll stop. Pretty much. So choose C as your answer. Hope that explains it. Question 7. A car traveling 60 kilometers per hour brakes to a complete stop over a distance of 80 meters under a constant braking force. Which of the following is closest to the braking distance required for the same car to come to a complete stop when traveling at 40 kilometers per hour and braking with the same constant braking force? Does it say the same braking force? Okay, so let's look at 7. So let's look at this part here first. This part here. A car traveling at 60 kilometers brakes. So convert all these to meters per second. So to convert kilometers, you're going to have to just divide it by 3.6. So that's going to be, let's write this. So remember, this is your initial velocity. So 16.6. And because it breaks, your final velocity is 0. And at a distance, it stops at a distance of 18. And remember, because it is a constant braking force, for both of these, it says that they use the same constant braking force, the acceleration should be the same. So your acceleration should be the same for both of these values. And let's find that acceleration using your SUVAT. So it'll be v squared equals u squared plus 2as. So that's going to be 0, 16.6 squared plus 2a, and s is 18. So what's that? That's going to be 16.6 squared to 18. That's going to give me an acceleration of negative 7.65 meters per second squared. This is your acceleration for both. So for the next question, all we have to do, whichever formula is closest to the braking distance required for the same car to complete a stop when traveling at 40 meters per second. So again, so your u in this case is changed 40 kilometers per hour to meters per second. So just divided by 3.6. That's going to be just 11.1 meters per second. And we want to find a velocity 0 because it brakes. We want to find the displacement that it's gone, but remember acceleration is the same because they're using the same constant braking force, which is negative 7.65. And so it's pretty much the same formula. V squared equals u squared plus 2as, v squared minus u squared over 2a. This formula is going to give us those values. So your v is just going to be 0 minus u squared, which is 11.1 squared, all being divided by 2a, which is negative 7.65. That's going to give us what? That's going to give us 8.06, which is A, pretty much. Nice. Question 8 and 9. Maya is given a light spring with an unstretched length of 20 centimeters. So the force versus extension graph for the spring is shown below. Maya hangs the spring vertically and attaches a mass to it so that the new length of the spring is 30 centimeters. So let's have a just draw at this. All right, so we have a spring. So its natural length, this natural length is actually just 20 centimeters. And so when she adds a, when she adds a mass, of course, it's going to spring more. It's going to be compressed. And this is your mass. And of course, it gets compressed by another 10 centimeters now. So imagine this is another 10 centimeters. Yep. And so the new length is 30 centimeters. So if you add these, yep, it's 30 centimeters. Let's have a look at this. The spring constant K of my spring is closest to what? So we actually have a force distance graph, compression graph. And remember that to find the spring constant, it's actually just the slope of this graph, which is, this point here is 0, 0. This point is, remember, make sure you change this to meters, not centimeters. So it's going to be just 50 times 10 to the negative 2, which is 0.5. 80. So it's going to, your K value is going to find that slope. So it's going to be 80 minus 0, 0.5 minus 0, which is going to be what? It's going to be 160. So C. Let's look at the next question. Question 9. Assuming that the spring has no mass, okay, the value of the mass Maya attached to it is closest to what? All right. So this here, when they've actually put that, mass, the spring is actually going to start to oscillate, but then it's going to come at its equilibrium position. And this equilibrium position is where the force of gravity, which is mg in this case, we don't know the mass, so we're going to just write mg, is going to be equal to the spring force, which is going to be acting upwards. And that's equal to k times change in x. These values are going to be equal because remember, these two forces are going to be added together and they're going to be equal to 0 because there's no net force. It's, it's not moving. So these values should be equal to each other. So mg is equal to k times change in x. So we don't know the mass, but we know g is 9.8. K is already calculated to be 160. And the change in x is the difference. And you remember, the difference between how much did it stretch? It stretched the thing by 10 centimeters, which is 10 times 10 to the negative 2. So calculating m using that, (1.63 kilograms, which is A. Done. Question 10. Neil travels at 0.67 c from Earth to a star Proximus, whatever, which is at a distance of 4.25 light years away, as measured by an observer. So if it is measured by an observer, if this distance here is measured by observer, this is actually your proper length. So L naught. Which of the following statements is correct? In Ning's frame of reference, the distance to Proxima Centauri is less than this. Okay, so in Ning's frame of reference, there's going to be length contraction. And remember, length contraction is L is equal to L naught over gamma. So this value here should be less than this over here, because it's going to be, length is going to be contracted. So in Ning's frame of reference, she's going to see actually the length contracted. So in Ning's frame of reference, the distance between Proxima Centauri is Centauri, whatever, is less than 4.25. Yes, it is less, because she sees it less in her frame of reference. That's correct. Let's look at the next one. In Ning's frame of reference, the distance between is more than 4.25. Nope. Its length is contracted. According to Ning's clock, the trip takes longer than the time measured by the Earth's base clock. Nope, it will take a shorter, because remember, length is being contracted. In Ning's frame of reference, the distance between this is exactly 4.25. No, length contraction has happened, so A to answer. Question 11. The star Vis is classified as a red supergiant. At the core of the star, 3 stationary helium nuclei fuse to form 1 carbon nucleus and 2 gamma-ray photons, as represented by this equation. All right, so we have, of course, 3 heliums, and they react, through fusion, and they create a carbon and 2 gamma rays, photons. The mass of 1 helium nucleus is this, and the mass of 1 carbon nucleus is this. The energy released from the fusion of the 3 helium nuclei is closest to what? So the energy released is actually these gamma rays. These are your energy released, those gamma rays. So we need to actually find that change in mass. What's the mass of these over here? Well, if I know that we reacted 3 of these heliums, so each of these helium has a mass of this, so 3 of these heliums times 10 to the negative 27. So let's write that. 3 times 6.645 times 10 to the negative 27. Is that right? That's going to be equal to 1.9935 times 10 to the negative 26 kilograms. So these two, by, conservation of mass, whatever this mass is here, it should be equal to this mass over here. So we have this mass, and it's all going to be converted to this over here. Luckily, we know that there's only 1 carbon that's been created here. So this over here, we minus that 1 carbon, and we would be left with those 2 gamma ray photons, and we just need to find the energy. So we have this 1.9935 times 10 to the power of negative 26, and we minus the 1.993 times 10 to the power of negative 26, which is this part over here, because 1 carbon will minus it, and we should be getting 1.9993 times 10 to the negative 26. That's going to give me 5 times 10 to the power of negative 33 kilograms. This is the actual mass of these 2 gamma photons, and now we have those, we can actually find the energy, which is using mc squared. So what's the mass? It's 5 times 10 to the power of negative 30 times c squared, which is 3.0 times 10 to the power of 8 squared. Let's do that. 3.0 times 10 to the power of 8 squared. That gives us 4.5 times 10 to the negative 13, which looks like C is your answer. Question 12. The diagram below represents a standing wave on a string fixed at both ends, with a node at the center. Okay, as you can see, this is a node where destructive interference occurs. The wave has a frequency of 5 Hz, and the distance between the 2 fixed ends is 2 meters. Whichever form would be closer to the speed of the transverse wave traveling on the string? Easy. Well, all we need to do is look at our formula sheet. So we know that when we have a fixed end, to find the, we're given actually the frequency, yeah. This is the formula. Frequency is equal to NV over 2L, where we want to find the velocity. This value of N is pretty much the number of these parts over here, So we have 1 here and we have 2 here. So we have 2, the n value is 2, so, well, the frequency is actually 5. The n value is 2. We want to find the velocity, 2, and the length of the thing, which is 2. Which is, you cancel those out, 2 times 5, which is 10. So your velocity actually should be 10 meters per second. Easy. 13. The refractive index of a diamond is 2.42 and the refractive index of water is 1.33. Which of the following is the closest to the critical angle for a diamond fully submerged in water? Let's have a look. So if we drew some water here, we draw like a full-on, something like this, like that. And so it's filled with water, and so imagine this whole thing's filled with water, and you have a diamond. So it's something like, diamond. Something like a diamond. Yeah, this is your diamond. Actually, let me draw it bigger. Let me just draw it as a triangle. Alright, something like that. So this is your diamond. And so we know that the refractive index of the diamond is 2.42 and the water is 1.33. Which of the following is closest to the critical angle for a diamond fully submerged in water? So I think, alright. So are they telling us, like, let's say a light goes to the diamond from the water to the diamond and hence goes to its critical angle? Is that what they're asking? Quite confusing, to be honest, this kind of question. So, yeah. So if we want the critical angle, this is your critical angle. It'll be, so this is where your normal is. Let's just draw a normal. The normal line. Yep. And so imagine you bring like a ray here. Let me draw a nice ray here. A ray. And so if we want it to be at its critical angle, it's going to be this over here, where the critical angle is. So, so if we're going from, are they asking us that? So are we going from the water? So N1, so this is your critical angle, by the way. N1 sine your critical angle is equal to N2, where N1 is, we're going from water, which is 1.33 sine theta C is equal to N2, which is inside the diamond, which is 2.42. So 2.42 divided by 1.33. And so sine inverse of that is, it's an error. So we've got the values wrong. Because, okay, and it makes sense. Because we're saying that, so we've just pretty much done something wrong here. We're actually doing the opposite. So your N1 in this case would have been that 2.42 here. And this one had to be N2. We're going to be 1.33. And so hence, yes. Let's try this now. 1.33 divided by 2.42. And then we use sine inverse. Now we get an angle, which is 33.3. So it looks like C is your answer. The main thing actually for this question is I was just very confused with how to graph it, but that's not a concern. Whenever you're doing critical angle, let me tell you one thing. When you're trying to calculate the angle, you need to look at this sine, theta C. These values must be between -1 to 1. Remember, sine is between -1 to 1. First of all, we made the mistake of first mixing these two up. Remember when we said 1.33 here, and we divided it by that 2.42. And so we divided both sides, by 1.33. So we got some value, like, I have no idea, was it like 1.8 or something? So this value would have been 1.8. Remember, sine theta C must be between -1 to 1. But this is greater. 1.8 is actually greater than 1. So that's why this is an error. It's impossible to get a critical angle like that. So you just had to make them opposite. Now, when you made them opposite, we actually got then 0.5. And 0.5 is between that -1 to 1 thing. So, and then we got our critical angle. Easy. Yeah, I think this question is ugly, to be honest. They should be more, like, they should give a diagram maybe to help us out. But yeah, but it wasn't too bad. Question 14. An unpolarized light ray is directed towards two polarizing filters X, Y, which are placed so that their planes of polarization are at a right angle to one another, as shown in the diagram below. Okay, which of the following correctly describes the direction of the electrical field vibrations of the light emerging from the two filters? Alright, so imagine we're drawing two Okay, so imagine okay, so we have a wave that's going to go like this in the vertical direction. And we're also going to have a wave, that's also going to go in the horizontal direction, like this. And as they pass through filter X, it's going to actually filter only the horizontal. Because remember, these are in the horizontal direction, and it's only going to filter that horizontal. And it's actually going to delete that vertical. And as it passes through filter Y, this is going to delete this horizontal. Because remember, this is a filter that has vertical and only lets the vertical ones pass. And so whatever this guy's seeing, he's not going to be seeing anything. Because, yeah. So let's have a look. Okay, so A, electrical field vibrations of light emerging from X is what? So the ones that are emerging from X is what? It's going to be like the horizontal. So vibrate in every direction or vibrate in one direction? It's going to vibrate in one direction. These were vibrating in many directions, like in a lot of directions, but this would vibrate in one direction, which is the horizontal. So B and A are wrong. What about the next one? Electrical field vibration of light emerging from Y. So here is what? He's not going to see anything. There's no light. So D is your answer. Done. Question 15. The Doppler effect can be observed only in sound waves? No. It's normally Doppler effect is used for mechanical waves also, like for all mechanical waves. So only sound waves? Nope. That's not true. B, in all mechanical waves? Yeah, that's true. Only in electromagnetic. No, electromagnetic is wrong. Remember, Doppler effect is used for, it has to have a medium for Doppler effect. Electromagnetic, don't have a medium, so those are all wrong. In water, waves and sound waves, but not in electromagnetic. Yes, not electromagnetic, but water waves and sound waves, that's like, yeah, being very specific, but it's for all mechanical waves. B sounds more correct in this term. Easy. 16. When light of a specific frequency strikes a metal surface, photoelectrons are emitted. If the light intensity is increased, but the frequency of light remains the same, which of the following will be correct? Now, we know that the intensity of light, if you actually increase it, it only increases the amount of photoelectrons, but it doesn't affect the energies. So, and if we remain the frequency the same, remember the frequency affects the maximum kinetic energy. If you haven't really changed that, if it remained the same, would be no effect in that kinetic energy. So number of photoelectrons emitted, would increase because the intensity of light increased. So these are going to be wrong, and the maximum kinetic energy of photoelectrons will remain the same. A. Question 17. Some of the energy levels of a hydrogen atoms are shown in the diagram below. A hydrogen atom has been excited to 12.8 volts, okay, and it returns to the ground state through 3 transitions. Yes, we can see figures 1, 2, and 3. All right, let's have a look. Which of the following indicates the energies of the emitted photons? Easy. So the first one is you're going from 12.8 electrovolts to 12.1, so you minus those, and that's going to be 0.7 electrovolts that would be released, emitted. So C and D are wrong, so that's the first one that will be emitted. The next one is going to be from 12.1 to 10.2, so 12.1 minus 10.2, which is 1.9 volts. Another one that will be emitted is 1.9 volts. So A is wrong because it doesn't have that. B looks right. It has 0.7, 1.9, and probably 10.2 minus 0, that's 10.2. Done. Question 18. Which of the following best describes how laser light is produced? Actually, this is in my summary sheet. Make sure to have all these in your summary. So in my summary sheet, you have it right, a beautiful section where I've put these over here. All right, here it is. So it says laser. So the cause of light for a laser is electron transitions in atoms in a gas due to a stimulated emission. So stimulated emissions. Which of the following best describes how laser light is produced? By focusing solar radiation. What the hell? Rubbish. By stimulating the emission of radiation. Yes, that's pretty much what I have in my summary sheet. The definition of it. So I'll put a tick on that. By accelerating positively charged particles. That's like a cyclone, or that's not particle accelerators. What the hell? No. D. By heating a tungsten filament in an evacuated glass tube. That's just incandescent light. So it's only B. 19. Diffraction is a property of waves. Electrons display wave-like properties when producing diffraction patterns. Yes, That's why diffraction patterns, when electrons actually display diffraction patterns, that's a proof of why electrons can behave as waves. This is because electrons always carry an electrical charge. Nope, does not explain that, why that's a diffraction. But so B, can move around in a nuclei in fixed orbits. That's explaining quantization. It's not really explaining why there's a diffraction pattern, so nope. C, have a wavelength related to the momentum. Yes, because we know how diffraction pattern is in terms of wavelength. Remember, so let me draw that. Yep. Remember, when we have diffraction pattern, we have wavelength. Sorry. We have like a wavelength. This is your wavelength. And so we know our wavelength is equal to, the formula for that is h over p. And p is our momentum. Yes, have a wavelength related to the momentum. Pretty much, yeah. Because we have momentum, we're going to actually have diffraction. So the wavelength is related to the momentum. That's great. So that could explain it. D, conjunct between energy levels within an atom. That's just Bohr's that has no like explanation for diffraction. So C is the great for that one. Yeah, have a wavelength related to the momentum. Beautiful. 20, last question. The position and the momentum of an object cannot be measured precisely at exactly the same time, no matter how carefully the measurements are made. They just describe Heisenberg's uncertainty. This is explained by what? Yeah, Heisenberg's uncertainty. Great. What a nice, easy question to end the exam. Beautiful. Yeah, what an actual beautiful exam, I'd say. Quite easy that year. So I hope you guys learned something through this video, and yeah, please make sure to like and subscribe for more videos, and share this with your friends. I hope you guys have a great day and take care of yourselves. Bye bye.